We're going to be talking about per unit quantities with transformers now. We've seen how to use per unit quantities, the basics of them in the earlier two videos. And we're going to talk about how to use them with transformers in this as well as the next video. And we're going to see how per unit quantities make calculations a lot easier in circuits that have transformers. Before I begin though, I just like to do a quick recap of what we've seen so far. First of all, we've defined per unit values as being equal to actual values or a base quantity that we define. Also, we saw that the four main electrical quantities we concern ourselves with are voltage, current, impedance, and power, and how, as long as any two of these are defined, we can calculate the other two using either the Ohm's law, V equal to IZ, or this formula for power, that power is equal to VI. So we've seen this in the earlier two videos. Also, one other thing that I'd like to mention and kind of just jog everyone's memory. We are all aware, we've all seen the transformer basics before, but these are important for today's discussion. So I thought I'll quickly run through these. We know a transformer circuit has a primary and secondary winding. Let's say the turns ratio is N1 by N2. Let's define that as being a variable A. Now, this turns ratio, there's a relation between the primary and the secondary voltages, the currents, the impedances, as well as the power that's defined by this turns ratio. We should remember that the voltage ratio V1 by V2, so the voltage on the primary and the secondary, is directly proportional to this turns ratio. The current in the primary over the secondary, that ratio is inversely proportional to the turns ratio. We know if there's an impedance on the secondary, that impedance would be seen on the primary. Let's call that Z1 prime. And that's defined by this relation right here. Also, we know that the power remains the same on the primary and the secondary side. So these are transformer basics. I'm hoping you've all remembered this from your transformer classes earlier on. If not, I encourage you to quickly review those once again. But since they're useful in this discussion, as I mentioned, I just thought I'll quickly run by them. One other thing that I want to mention is in the earlier videos I mentioned impedance base. When we are defining that is just um, square of the voltage base over the power base, right? We just have that relation from just manipulating these equations right here. But you need to be careful when you're dealing with units here. What units is voltage defined at? What units is power defined in? So this formula, if you put the units in, is and mostly you're given power voltages in, let's say, kilovolts, and power in either kVA or MVA. So that is just basically kV square over MVA, or it's kV. There should be square there. kV square over kVA times 1000. The reason that is because kV square is nothing but 1000 volts times 1000 volts, right? Which is basically 1 megavolt, and this 1 mega here cancels this 1 MVA mega here, right? And that's why this relation holds true. So you got to be very careful when with your units when defining your Z base. And we'll use this in this example that we're going to solve right now, so it'll become a little bit more clearer. So I'm going to solve an example, and using this example we are going to see the beauty of per unit quantities with transformers. So let's consider a transformer. Let's define let me draw a circuit for you here first. So we have two transformers that I'm going to draw in our circuit. So that's one transformer, then you have your other transformer, and then you have your load, let's say here, right? Let's say this is transformer 1, this is transformer 2. Now these are almost three separate circuits. They are physically separate, right? They're electrically connected through the transformers, but they have different voltage levels on all these three different circuits, right? So this is, let's say this is circuit 1, this is circuit 2, and this is circuit 3. Let us then define this as Z3. Let's say this is 100 ohms. All right. And we are given that T1 is a 1 MVA transformer with a voltage ratio of 5 kV on the primary and 10 kV on the secondary. T2 is again another 1 MVA transformer with a 10 kV primary and a 2 kV secondary. And we are asked to find what Z1 prime would be and what Z2 prime would be in ohms and in per unit. All right. Now remember Z1 prime and Z2 prime, what they are. Z2 prime is basically this impedance as seen in this circuit, and Z1 prime would be this impedance Z2 prime as seen on the primary of this transformer, so on circuit 1. So we are asked to find that in both ohms and in per unit. So let's see how we can go about doing that. Let's first find Z1 prime and Z2 prime in ohms. That should be easy to do. We know what Z3 is, and we know this formula right here. So going by that, we would say Z2 prime is nothing but A2 square times Z3. Now what is A2 square? A2 square is nothing but the ratio here, right? So A2 square, okay, this gives me A2 is 5 and this gives me A1 is 0.5, because remember voltage ratios are directly proportional to your turns ratio, to this quantity A. So to find A, I just do V1 by V2, and in this case again V1 by V2. So I get my A1 and my A2, right? So my A2 is nothing but 5, so I do 5 square times my Z3, which is 100 ohms, which gives me 2500 ohms, right? Now my Z1 prime is A1 square over times Z2 prime, right? Because here the impedance is nothing but Z2 prime. So this becomes 0.5 square times 2500 ohms, which I believe is 625 ohms. All right. So we've done first part of what we were required to do to find these two quantities in ohms, right? Now let's try to do the second part where we're defining these two quantities in per unit. To define anything in per unit, we need to first define the base values, right? So let us begin by defining the base values. Define base. Okay. Where do we have three different circuits here, right? Let's start by defining base values in circuit 1. So let us say our voltage 1 base is 5 kV. Remember, these are values we're defining, so we can choose any values we want, right? And then my power base in circuit 1 is 1 MVA, which implies my Z1 base, again referring to this here, is going to be 5 kV square over 1 MVA which makes this 25 ohms. Correct? I believe that should be correct. And then, now, what about circuits 2 and circuits 3? We could go ahead and define some bases there as well. But what does our intuition really tell us? These circuits, as I mentioned, are physically separated, but they are not electrically separated. We have formulas which connect voltages on a circuit 1 to circuit 2, right? These equations right here. So what we can do is we can calculate the remainder of our bases in the remainder of our circuits. So we can do that using this calculation. What we can say is my base in voltage base in circuit 2 using this equation right here is going to be voltage 1 base over A1, which makes this, sorry, let me just erase that 1 second. Voltage 1 base is 5 kV as I defined by A1, and my A1 value is 0.5 here. So that gives me 10 kV. Power remains the same. So I'm going to say my S2B is also going to be 1 MVA, which implies my Z2 base is nothing but 10 square over 1, which is 100 ohms, right? Similarly, I'm going to get my V3 base as being V2 base over A2, which is 10 over 5, which is 2 kV. S3 base is equal to 1 MVA again, which implies my Z3 base is going to be 2 square over 1 is going to be 4 amps. Alright, now that I've defined all my base values that I'm interested in, I didn't do current here because current is something we're not really interested in this problem. We are not using it anywhere. So let's define our per unit values. Let's calculate them. Z3 per unit would become 100 ohms because that's the actual value, right? If you go up here and see the circuit, 100 ohms, right? So that would be 100 over this base of 4 gives me 25 per unit. Z2 per unit is equal to, or let's make that Z2 prime per unit is Z2 prime over Z2 base, which is 2500, right, over 100, which gives me 25 PU. Z1 prime per unit is equal to 625 over 25, which gives me 25 per unit. This is the result that I wanted all of you to see. All our impedance values in per unit are the same, and this is the beauty of using per unit. What this is telling me is that if I use per unit values, my impedance value, this load impedance in circuit 3, is going to remain the same. It does not change whether I see it in circuit 2, whether I see it in circuit 1. Whereas if we were doing ohmic values, it was 100 ohms here, it was 2500 ohms here, it was 625 ohms here. But in per unit, it remains the same. What that means is I can basically get rid of my transformer. So if I was to draw an impedance diagram, for that circuit up there, it would look something like this. This is my transformer 1 impedance. I have not mentioned there's no impedance given for those transformers, but both these transformers would have some impedance. in per unit, and then that is Z3PU. And I can just solve this circuit with the bases that I've calculated, right? I can just solve this simple circuit. I do not need to consider the turns ratio anywhere, none of that. I solve this circuit, whatever voltage current values I get, I can use these base values to calculate what that voltage, and to convert that per unit I'll get per unit values of voltages and currents here, right? If I solve this circuit, whatever per unit values I get, those will be converted to actual values using these base values for these individual circuits. And we will see this in the next video that we do. We'll discuss that in more detail and see how to use our findings from today. But that's the interesting result that I wanted to show you guys. The key here is choosing the bases correctly. So the key takeaway from today's example, the key takeaway is we can get rid of the transformer if one, the MVA base remains the same across all circuits, and the kV base is determined by the turns ratio determined by A. So that's the key takeaway from today's example that we did, and we will see this being used in another example next video. But before that, I want to leave you with a sample problem, as I always do. So I'm going to leave you with let me do the sample problem in another color so it's easy for you to differentiate. Oops, give me a second here. All right, so I'm going to leave you with a sample problem. Let's say you have a 3-bus system, and I'm going to make this a little bit interesting, but I'll probably give you a hint before I leave you guys. This is a 3-bus system: bus 1, bus 2, bus 3. This is a load here. This is your transformer 2. This is your transformer 1. You are given that your load value is 1 kilo ohms. So basically 1000 ohms. Your T1 is, let's say, a 100 MVA transformer with a 13.8 kV primary and a 138 kV secondary, and it has an impedance of, let's say, 10%. And so let me define that as ZT1. Transformer 2, again 100 MVA. Remember, this is not impedance in the circuit, this is the impedance of the transformer itself. Transformer 2 is again 100 MVA transformer with 138 kV primary and let's say a 4.16 kV secondary. The transformer impedance for this transformer is, let's say, 8%. What I want you to do I'm also going to give you base. So I'm going to define voltage to base as being 100 kV, and I'm going to define the S2 base as being 100 MVA. Now what I want you to do is I want you to find what is Z1 prime in per unit, what is Z2 prime in per unit, what is Z1 prime in ohms, what is Z2 prime in ohms, and I want you to draw me the impedance diagram for this circuit. Okay, so I said I'll give you a hint. All right, so let me draw this similar to how I drew my circuit in the example. So this becomes nothing but, okay, a funky looking transformer. So that 3-bus system that I've shown you there can just be drawn like this. So this is your load of 1 kilo ohms. That is your T2. That is your T1. This is your circuit 1, circuit 2, circuit 3. So this should make it very clear and very simple for you to solve this. And I hope to see your answers in the comment section below. If you have any doubts, if you have any questions, feel free to ask me. Just leave a comment, and hope to see you for the next video. Thanks. Take care.